तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We will take another design example for implementation on FPGA board, the real time clock, and it has quite many applications right from real time display, and using which you can show in 24 hours or 12 hours time range, and what you see is the hardware here for the same, and you don't notice that there is an FPGA board and also a digital IO board, and of course there are power supplies, the details of which we will be seeing after lecture or two. And let us get into the basic applications. Apart from this real time display, we can have up counter or a down counter, and we can use the same for an industrial or photographic timer, or you can use the same timer with 3 different alarm settings for medical treatment, so which demands the administration of medicine on timely basis. See, for example, for patients like epilepsy, they are prone to fits and other attacks, and if they don't take medicine within 45 minutes to 1 hour, and needless to say, this will prove a big very useful thing for such patients. And the features of this real time clock is as follows. So what we have designed is 24-hour clock, and you will be requiring to do convert it into 12-hour clocks later on, and when we deal with the assignments for you, and it has hours, minutes, seconds, push button settings, and you can have 3 independent push button switches to set the same, and you have a stopwatch which can count up or down, and count setting by push buttons. You can set the up counter or down counter by using the very same push button that you have used for this, and there is also a timer out after having run out of the timed out. So that is after running the set time, be it in up counter mode or down counter mode, when it finds the match with the set time, this timer out signal is this also a single bit output that will be turned on. So you can use this for example for firing a rocket. If you wish to, you can either have a down counter, and when the time is all zeros, you can fire the rocket, and the timer out will go 1 and remains as such. And if you don't like this mode, you can have a real time counting in up counter mode, wherein you can actually see the real time, and this, when the set time matches with what you have already which is running, which is the same as the running time, if it matches with that, once again a timer out will be issued, and you can use any of these two as per your real application. We have 3 independent alarms that can be set using DAP switch, and alarm settings can be done by push buttons as we had done for the up counter, down counter or time mode setting. And there is a common audio alarm. Alarm is used making use of a piezoelectric buzzer. And when you design a system, what is important is the conception of the product. What will be your end product, that must be borne in mind. To start with, as a layman, if you are out on the shop to buy a particular, say, a clock, so you will be looking at only the display, not the inner details as to whether you have used a controller or any other embedded system or whatever, a microprocessor or FPGA. It does not really matter as far as the customer or user is concerned. He is a common man, layman, and who does not know the intricacies of the design involved. So you should always, as a designer, think from that point of view when you design a system. So what appeals to our mind is there must be you want to do a real time clock. You want to have it as a on your bench, right? Let us say we wish to put the real time clock right on the tabletop, and naturally you need 6-digit display for the same, say hours, minutes, seconds, and when you have this, there must be a provision to set them. So you can have locate the push buttons right beneath this and name it like this. So what is important is the layout is quite important, because it will be very easy to learn how to operate this from the common man point of view. And there is a buzzer, and which is a piezoelectric buzzer, and there is a timer out LED here. In addition to this, you will also have an output, and we have already seen making use of ULN 2003. So you can trigger that particular thing. This timer out can be connected to 2003, one of the outputs, and the other end of the ULN 2003, which is a Darlington pair open collector, you can connect it to a solenoid or a relay, and or a solid state relay, whatever, and so that you can connect any real time output. For example, for a photographic exposure, you can connect this timer out to the actual lamp, which really exposes the film, and you can use for the same thing as well. And you also need other controls. For example, you want to have, there are so many modes such as time mode. So you can, if you want time mode, you can set using this here. Down position is the time, up position is the stopwatch, and once you have this, you also need whether the time must run or stopwatch must run. If you put it in run stopwatch and mode, it naturally it runs the stopwatch. If you want to set say time, you put it to set here and then let it be in time. If you want stopwatch setting, set stopwatch is all that you have to do. So as you see, so it is. So that will be the most simple thing, even a child can handle it. And if you design bearing in mind the ease of handling as far as the common user is concerned, and you have an up counter as well as a down counter, and you have a switch for that which you can set to up or down, and similarly you need an alarm. So these two are earmarked for alarm. You can switch off the alarm or switch on the alarm. This is only to switch off the actual audio alarm. This does not really reset whatever you have set, and you can set these alarms. For example, there are 3 different alarms that you can set, alarm 1 through alarm 3. Of these, topmost priority is AL1, alarm 1, and AL3 is the least priority. And you can, if you take to this position, you would be setting or reading the respective alarm. And you also have one set and read. This appears to be redundant. It's not really so, because we also need to have the same controls for the stopwatch also. Once again, in stopwatch you have an up counter as well as down counter. So perhaps if you give little more thought, you can save some of these switches. But I did not make much attempt in reducing, because these switches are already available on the hardware that we have already used for the traffic controller earlier. And in addition to this, if you want to reset, normally this will not be provided for the user. this will be with inside the unit, but just for the sake of completeness I have put it here. In fact, you should conceal such resets from being tampered by the normal customer. So this is what we have the goal in mind. With this in mind, we should go for what hardware is available, especially at R&D stage. Just as we are right now, we are trying to learn the design, not the actual the product that is going direct to the market. So we are on the development stage. So even then, nevertheless, we should have to start with this and then go to the actual hardware that we already have. We have already seen the use of a digital input output card, and if you notice that one, we had 6 digits there, and I am not going into the details of this because I have already explained to you how to use this, and they are all socketed totally, so that we can configure for any other application. Very same board such as digital IO or FPGA board that is going to follow suit will can be reconfigured for any number of applications, of course subject to the limitation of the hardware that you have. And what all you need in this digital IO card is only this 6-digit display, and you note that I have just marked hours, minutes, seconds, which was not there earlier when you had seen the last time, and it's only to earmark hours, minutes, seconds, and use only 6 digits and nothing more on that board. And on the FPGA card, we have a 8-bit DIP switch, and we have already seen the setting earlier. What we want, what our goal was this one, and naturally you can't get one-to-one correspondence. There may have to be a slight difference when you configure the same thing, because the hardware is already done and you have no choice over the this. So as far as possible, I have retained the very same arrangement for all the switches, except that reset is part of the DIP switch here, and which was shown as a push button switch in the previous layout. And you have hours, minutes, seconds right at the FPGA board left hand side corner, and they are all numbered SW4 through SW1, and there is one more switch here, so that we may start or stop the up counter or down counter, which we have. This was also there depicted in the earlier layout that we have seen, and these are naturally push button switches, and this is a DIP switch, and we have wantonly suppressed all other hardware on the FPGA card. And in addition to this, we need one more switch, and that is alarm on and off. So this is a separate switch here, what is there on the board on the your right end, right on this, it is there. So now let us go into more details. First we have to formulate a specification. So before we specify anything, what we want to do, we are going to make a chip. So we need a block diagram for a chip. For example, this chip will have to have different switches that you have already seen earlier, and for example, in addition to that, you need some more signals. For example, you need a system clock, and you need a reset, which was already there, and we need a run set switch, which was shown there. And now notice that I have just added one I here, because this is the block diagram, the pin diagram as such, and this is what we want to implement on the using Verilog. And while using the Verilog code, we are going to precisely use the very same nomenclature and nothing different from this. So for that, we have very many such signals. For example, I run will be there, there will be R run, and simply run set, and so on. So we will have 3 variants for each of these inputs, that we will see the details later on. And we need a time stopwatch, and all these switches you have already seen. So I will quickly go through this. And you need a down, up, and I stands for the input. That is what this is the physical input pin that you have to connect. And you need 3 push button switches for hours, minutes, seconds setting, and you need to start or stop if you are in up or down counter mode. And if you want turn on or turn off alarm, you have this switch. Then if you want read set the alarm, you have this another switch. And for 3 independent alarms, you need 3 switches here, alarm 1 through 3. And as far as the output is concerned, rather outputs are concerned, we have 6 digit of 7 segment display that you have already seen, which I hope is running on a corner. What is running there on the corner is a display for down counting. For example, the application for this for this studio demands 50 minutes program. Every episode is going to come as a 50 minutes for you, and we have just when we started we have switched on the down counter. I hope it is running at some corner, and so when the time is over it will be 0 and it will stop as well as give the buzzer output, and that is the purpose of this stopwatch, using the very same hardware we had done for this particular studio application. And coming to the display, those 7 segment displays are 6 in number, display 1 through display 6, and each of which is 8 bits in width, and we will go into more details of each of this, what each bit is doing. And we need 7 segment plus 1 decimal point also, and so that takes 8 bits totally. That is the reason why we have 7 through 0, that is 8 bits for each of the displays here. And we also need a beeping sound alarm. So what we had to do is we had to create a square pulse, and that is what is output here in beep, and this is connected straight away to the ULN 2003 or 74LS05, I think the latter, and output of which is connected to the buzzer, and buzzer operates at around 8.5 volts, which happens to be the power supply for the FPGA board that we use. And this naturally the pin diagram, or you can regard it as a block diagram of the real time clock. And you have finally one more output for timer output, which we have already explained. So next is the actual signal description, some of which I have already described. So I will quickly go through each of this here. So clock is a system clock, then reset is asynchronous, it is active low, as we have used in very many design examples or applications that we have seen before. And you have a run set switch, then time stop switch, up down switch, then push button switches for hours, minutes, seconds, then a start stop push button switch, then sound alarm on off, which is common to all the 3 alarms. And this this switch, that is alarm read set, is enables reading or setting of the alarms, and you can set or read or even switch off the alarm 1 or alarm 2 or alarm 3, as you have seen listed here separately. And there are obviously 6 digit displays, which we have already seen, and here what it means is display 1 is the hours, so also the display 2. Hours will be on your left side that you are seeing on the stopwatch running there, and that will be the most significant digit onto the extreme left, and that is display 1 or counter 1 that we are going to see when you look into the actual Verilog code. And so is the case for display 2, which happens to be just the LSD hours. So is the case for minutes, and there are 2 digits once again, MSD and LSD, corresponding to display 3 and display 4. 5 and 6 are MSD and LSD respectively for seconds display. And you have a beep alarm, which we have already seen. The last timer out, this is switched on when the set time expires in up or down counter mode. And so there is a note here, I will just read it out for you. Only on one of the 3 alarms can be set or read at one time. So you can't do all the 3 simultaneously, you have to do one thing after another, and if more than one is set, the highest priority alarm alone will be actually set, and others are totally ignored. Alarm 1 is the highest priority, alarm 2 is middle of that, and then alarm 3 is the lowest priority. So what we have already seen, we are seeing once again, and this time it is going to be little different. So basically now we are going to start the Verilog coding. Prior to that, you should grasp the fundamental principle of the design. So what we do is, this is basically the same pinout that we have already seen. I am not going to these details, and what here is, it was display 1 through display 6 instead of display 1 through display 6, that is actually here, and this is what is going to power the 7 segment that display that is running right now there. So now if it is in stopwatch mode, we are going to use counter 7 through 12, which is the case for this particular example that you are seeing. The running stopwatch is using counter 7 through counter 12, and counter 7 corresponds to display 1 in the same order, hours, minutes, seconds. It is exactly the same order that we have seen for the display, and so is the case for counter 1 through 6, except that this is going to show the actual real time. So your watch display that you have, the real time that you have will be through this counter 1 through 6, and one of these will have to be routed to this display, and that is done by a mux here, and these are all the so many bits of information is going here or here. This mux is the selector, it will select either this or this depending upon this control, and this is not as simple as just single signal. There are multiple signals there, maybe 6 signals or something. When we go into details we will see more about it. So it is enough to say that we are primarily they are in either time mode or in stopwatch mode. If it is in time mode, let us say if it is 1, so counter 1 through 6 is routed to the connected to the display that you see there. Otherwise, that is when stopwatch is on, when it is 0, let us say. So this counter 7 through 12 will be routed and 1 through 6 will be off, right? And this is the simplified architecture of real time clock. So we have seen in any design how a customer will have to look from his point of view. We have to look and fashion it, and then go on to the architecture, and if there is an algorithm you have to do, as we have done in detail for MPEG, JPEG, making use of DCT quantization earlier, which we have seen elaborately earlier. And same is the approach for this design as well. For any other design, I strongly recommend from my own experience that you adopt similar such strategy. Now we are going into the Verilog code. So let us, this is the Verilog code for real time clock, and the design file, you have to put this particular design is going to be more than almost 2 hours lecture for this, the code that is going to run. And so please stop me at any point of time you are not clear, because we are going into more and more intricate details. It is like entering a labyrinth, let me warn you, so follow it very carefully. And you need this particular file is a design file, so we will nomenclature by the common names. For example, I want an alarm also, so 3 alarms are there, so I nomenclature it as RTC, standing for real time clock with alarm facility. So .v is the Verilog file, the file that you are right now seeing is the .v. You have to locate all these Verilog codes, which is the same as writing any other C program, except that this is hardware design language, not a software design language. We have seen couple of, very many number of times the difference between C and this. So I will read out the comments here, and you also need a test bench to test this one. I have not written a very elaborate test bench. I will explain for details, further details later on, and that will be RTC underscore alarm underscore test.v. This is the test bench. In order that we may test the design, and this is the design for a real time clock to display time as well as a function as a stopwatch. In the latter mode, it can count up or down, and up to 3 different sound alarms can be set. Timing range is I have separate out hours, minutes for ease of reading, although it is not so in the hardware that we have here. This is a 24 hours timer, and it will go right up to 23:59:59, after which it will go wrap around this and keep on going for eternity, so long as there is power available to the system, and it's in the same hours, minutes, seconds. For more details, see specification sheet. We have actually come through the specification sheet right now what we have seen. If you have doubt, go back to specification sheet and do it. And the code, real code starts here, and here first we had to we are going to use only one sub module, which is display ROM. It is a code conversion from BCD to 7 segment LED outputs, and basically what is going to run as the timer is, or counter is, counter 1 or counter 7 as we have seen before, and that will be 4 bit in width, and that will have to be converted into 7 bits actually. There is one more bit also earmarked for the decimal point that right now we are not going to use in this particular project. Probably as an assignment it might come, I am not very sure about it. And we had to include that sub module here, that is why we say include, and we also need some variables. For example, I want to keep track of how many milliseconds have passed, or how many seconds have passed, or how many decimillisecond, which means 0.1 millisecond has passed. This is for 0.1 millisecond. How much time has elapsed, we have to keep track of this. For that we need to define, it simply means DMS underscore base is equal to 1999. This is what it means here. We are going to operate at 20 megahertz operation, and the time base is 0.1 millisecond as we have seen, and that is this one. And if you want to change it for simulation purposes, you can make, instead of 1999 you can make it as 9, so that you can run much faster, and otherwise it will be an impractical task for you to run the test bench, because we are no longer dealing with a small number, but almost astronomical numbers we are dealing with, because hours, minutes, seconds, and again from 20 megahertz onwards we have to start counting. That means 20 million count, then followed by 60 for seconds, 60 for minutes, and then 24 hours. You see it has already skyrocketed to astronomical heights. Okay. So writing an elaborate test bench will be a very difficult affair, and we need another definition. For example, decisecond also we need, for which we need a 23-bit counter later on. For that we need to set here, and this setting is here. For 20 megahertz operation, the time base is 0.1 second, because decisecond implies 0.1 second. For 23, that all 19s setting, this is what is required for 20 megahertz. So it counts right from 0 to this one. So I have, as we have done for non-retrieval mono shot earlier, here also it demands from going from 0 through whatever is the last count here, 1 followed by so many 6 9s. And if you want, normally the FPGA card will have a crystal oscillator which may not run very accurately. In fact, this particular has some inaccuracy, so we have to fine tune it. Fortunately, we have the software way of fine tuning, and that is simply done by changing this value, right. Instead of theoretically you should have put 1 followed by all 9s here, but I have put here so that I get an accuracy within less than a second for this 50 minutes. I hope you are timing in your watch and cross checking whether it is really true, and I have checked couple of times. I am satisfied with that. I think it's 0.5 second or even less is the accuracy that you get, and we need to define time base, which is seconds, and we put only 9 there, because we are going to count only that 0.1 second, and here if you count 10 times 0.1 second you get 1 second. That is how you get a 1 second time base. And similarly for debouncing the switch we need 3 millisecond, and we are going to derive this from DMS, what we have already seen, decimillisecond, that will serve as the time base. And if you count 30 for that, 30 into 0.1 millisecond is 3 millisecond. You would have made 3 millisecond debounce time. And the actual module starts here. We declare the module name. This is the actual design module, RTC_alarm. It lists all the IOs that you have used, which you have already seen in the architecture, clock, reset, run, and so on. I am not going through that once again, just have a look here. And I have also put a comment here to mean what it is. For example, if you take alarm off on, one nomenclature I have given, as I had done before for all other design examples earlier, this N stands for negative, rather it is low, and that means this is single bit signal. If it is 0 it means on, if it is 1 it means off. That is what the comment says. For all of them it is exactly the same. So is the case for alarm. Then display 1 through 6 are there, and there are 7 segment LED displays. Display 1 through 1 and 2 for hours, 3 and 4 for minutes, and 5 and 6 for seconds. 1, 3 and 5 are MSD, all other things displays are LSD. So you need a beeping alarm, and a highly recommended thing is piezoelectric buzzer, which is a miniature thing which you see on the hardware there. And you also need a timer out, and this completes the module declaration there. And we need to, what all we have put inside as IOs, we are just listing here. So I will quickly go through this here, and it is for you to grasp it totally. So this have been already described to you, so I do not have to go through that. So hours, minutes, seconds, start, stop, push button, and this is alarm off, on, and then 3 alarms that you have, and only one of the 3 alarms can be set or read. If more than one is set, the highest priority alarm alone will be actually set, and others are ignored. Alarm 1 is the highest priority, alarm 3 is the lowest. In the specification we have seen, although we have seen exactly the same thing, so there is no harm in putting the same thing in the text also. When you write the code, you are not merely writing for your own sake. You do not want to just pass your examination and go away. It is to serve for all others who are going to use this subsequently. Some other designer will come and would like to change your code for some other application. So don't you think you will be doing a great service if you put the right comment? That is why I have been emphasizing that you put the right proper comments all through. If possible, line by line comment. I think I have adequately put comments. If it is lacking, let me know so that I can improvise on the existing ones. and then these are all the output declaration. It is 8 bits total. So, you see display 1 through display 6, and we have beep single bit, therefore, that is nothing here, and whereas 8 bits are described here in this fashion. And so is the case here for display 1 through beep and timer out are the two outputs, single bit outputs, and now you need to declare wherever you have used signals in assign statements, that will be a wire in the design which we have already seen earlier in several examples, and width is declared here. Display 1 through 6 is declared as wire, because finally you are going to use an assign statement for the same. And similarly, there are so many other wires. For example, I want a counter for decimillisecond, 0.1 second I want to keep track. So, I can do this by running a counter which is 13 bits, and you can arrive at number of bits by simply using the calculator that you have on your desktop on the computer, and that is how I have arrived at this one. You should know how much maximum that you need to go, accordingly you have to set the number of bits. So, is the case for decisecond. Decisecond is a mighty huge figure, because you need 23 bits, because we need to have 20 million tracked totally, and that is why this much. Then if you want a counter base which is in seconds, you need just 4 bits, because 0 through 9 only we need to keep track, because all other fine things timing is already kept by this, and this is going to refer to this, and similarly this is going to refer this counter DMS, and in order to keep track of 3 millisecond debounce time, and for which you need just 5 bits here, because it is going from 0 to 31, you need 5 bits. So, that is how you arrive at the accuracy that you need. Then you declare other wires, for example, decimillisecond, time base in second, run time, set time. I will quickly go through all this, because there are quite many of them, and set stop, I will just read it out, and when we come to that respective signal, we will describe what they are. Run stop, then advance hours, minutes, seconds, advance hours as well as time, advance hours, then stopwatch, then advance minutes, time, stopwatch, then seconds similarly, then time and stopwatch is there. You need to reset counter for certain condition, then you need this wire for reset counter 1 through counter 6 here, and 7 through these are all 1 through 6 is for basically for the running timer, and counter 7 to 12 is for the stopwatch, up down counter, and they also need resetting when the occasion demands. So, counter 7, and you also have to discriminate whether it is in stopwatch mode or in set mode, and these are all the signals, intermediate signals that will be needing in order to fulfill your total design, and so is the case for 9, 10, 11 and 12, and you also need presetting. For example, after you go to the fag end, let us say 9 is the last, after that it should become 0, or if it is down count mode, you may have to go 9, 8 right up to 0, after 0 you have to wrap to 9. So, that particular thing is called preset, and normally this is used for the down counter mode, and 8 through 12 is for presetting the same, and then you have counter 1 through 6 for advancing. When should you advance the count by 1? That is what it means here, and once again for counter 7 through 9 you have similar things as you have seen for preset and advance, reset. Now this time it is going to be advanced by 1, and once again it depends upon whether it is in set mode or stopwatch mode, and right up to counter 12 you need advance. And then next comes we have been using always statements for realizing registers. A counter can be realized by that also we have seen in very many number of applications. We are going to continue the same trend even in this design. So, it is once again this is a very good example for counter based design. It is full of counters and nothing more, and simply by using assign statement and always statement, the entire Verilog can be contained. You can be fully RTL compliant just by using this. So, learning time for Verilog is actually dramatically reduced if you just stick on to this, and you will also conform to RTL coding guidelines, which will certainly work in the hardware. Otherwise, you are not guaranteed of its working on the hardware, right? I overemphasize rather. and you need to keep track of the counters and you need to do the pre-incrementing. So that is what we do, and by having a separate counter running for that, once again it is also 4 bit in width, and they are still wires using assign statements, counter 1 through 6 here, and this will be used for pre-incrementing the actual counter 6 underscore reg, which is the real counter, and so counter 7 through 12 here is serving the similar purpose for the stopwatch, and then further wires are there. You have plenty of them. We had to wade through these signals, unfortunately. So we have probably we are halfway through declaring, and then we have another signal for run stopwatch down mode. So when it is in such a mode, we activate another signal, and so that once you give like this different meaningful signals, you can use it when the occasion demands. You can straight away borrow this signal there and do the logic there, rather than write a long code each time, right. That is the reason why we are using so many intermediate signals. And then also you have in this mode, if you want to reset the counter 8, we need one more signal. Similarly, you want to reset the counter, I think it is in this is while the stopwatch is running, I suppose, is it correct? So then if you want to decrement the counter 7 through 12, you need these signals here, and if you want decrement 7 through 12, you and this is just like we used pre-increment, we are going to use a pre-decrement counters before we assign to the actual register, which is counter 7 underscore reg, right. D stands for the decrement here, and once again the bits are same, and now comes the declaration of registers. Registers, as you know, are the signals that we use in the always block, whether it is combination logic or sequential logic, right, and whatever is appearing in as signals within the always block will have to be declared as register, and we need data 1 through data 6 here, which is the one signal for to mean either counter 1 through counter 6 or counter 7 through counter 12. We have seen right in the simplified architecture routing one of the two, and this is precisely that signal which has that single output directly fed to the display, and we also need 13 bits counter decimillisecond as a register, right. Similar names might have appeared, but there are slightly different signals, so it might be a next signal, and I hope there are no duplicates. If there were any duplicates, it would have shown up as some error or warning. I did not see anything. If you happen to see any of them, you can please correct that. Then for decisecond you need 23 bits, and they have to be, this is the actual register which is going to run, and for time base 1 second this is register, for debounce counter this one, and now comes we have already used I run set. Run set is the actual switch, I run set is the actual physical signal that goes into the chip input, and within that one we need a register so that we can know the current value as well as compare with the previous value, so that we can know when the transition has made. For example, if you push a button, how do you recognize the button being pushed? Only if you keep track of, continuously monitor its status at any point of time. If you read 0 for that push button switch, and later on if you read 1 for the same thing, you recognize that the push button has been pressed. That is how you recognize. For that you need to store in register, and so this is nothing other than I run set, but with a delay, and this has been registered when the clock strikes, right, and that is the nomenclature adopted all through. R stands for the register. It is nothing other than the actual input signal with a registered, it is registered inside, so that we may keep track of any transition that you make. Otherwise you can't recognize a push button being pressed, right. And for time, stopwatch, down, up, all these registers, what you see down all here is what we have already seen as inputs, and hours, minutes, seconds, start, stop, all are registered. So is the case for alarm, off, on, and 3 alarms, and they are also registered internally here. And in addition to this, they actually in the layout that we have already seen, we use only run set, and we are going to precisely use the very same variable name, or rather should not use this variable because it is C domain, right. Coming back to hardware domain, we speak in terms of signals, right, and habits die very hard, right, it is reflected in my own sentence. So just beware of that, refer it to as a signal. So here what is R run is actually run set after doing the debouncing. It has to be debounced, and you have to write appropriate code for debouncing, which we will be seeing later on. And all this we see is precisely the very same input or reg with the same name, but now what it implies is it is the debounced switch condition. So which is actually the same as what we have started with the layout for the common man, right. Very same symbol we are going to use hereafter, this will be used extensively. So is the case for hours, minutes, seconds push button switch, and this is also a push button switch which says start stop. If you push the button once, it will be in start mode, and if you put the same button again, it will be in stop mode. So just with one push button switch you can play dual role there, right. You have an alarm off on, once again off, and notice that on is low, this is a single bit. So all of them are single bits. So is the case for alarm, read and set. You can either read or set the alarm, and there are 3 different alarms, and these are precisely that. And now we also have 4 bit width counters. This is the actual counter which is really running for your time, right, and reg, notice that one. Earlier we have used next, that was declared as wire, whereas here it is declared as reg because we are going to use this in always block, and 4 bits here, and counter 1 through 6 for hours, minutes, seconds, and for if it is in stopwatch mode, exactly same hours, minutes, seconds, counter 7 through 12, and they are also registers, and start stop reg and start stop and hours, we have some more here. For example, this you are already familiar, start and stop, and when you press, we should know what was the previous value. That previous value will have to be a different register, so exactly same name with P here. So this implies it is a previous, only then you can, by comparison of the two, you can know, recognize when it has been pressed. Similarly for hours previous value, hours underscore delay is what we are going to explain later on, and this is in the setting mode, and on delay output hours, we have what is called an on delay timer, and that output is this one, which we will be needing at the time of setting the hours display. And similarly you need 2 seconds delay, so that when you want to advance, if you press the push button once, it will advance by 1. If you keep it pressed for 2 seconds minimum, it will automatically run 10 times faster, so that long displays, long time display, you need to you can set it fast, so it runs at 10 times the normal speed. Otherwise it will run at 1 second, every time you push it will run at that every time you push, and when you near the targeted value, you can stop before that, releasing the button, and then advance it by pushing once, so that you advance step by step. This is what is in the market, maybe a Philips 2-in-1 you would have seen, where real time display is also available. Precisely they have used such strategy there in order to set. So is the case for minutes and seconds, again 2 seconds, and all are exactly the same. You also need advanced reset counter 2, and this we have not covered before, so we need to declare that as a wire because we are going to use it in assign statement. And reset counter 2 time, counter 2 set, then reg temporary, we need temporary alarm registers, and for 6 different alarm displays we need temporary registers. So it is exactly same as counter 1, counter 2, and so on. For each of them you need a temporary register, so that we can do the alarm setting. For each of the, there are 3 different alarms which will be set in using alarm reg 1 through and so on, and this is the pre-increment as you have seen next earlier also. So we have 1 through 6 here for temporary alarm setting here, and we need advanced temporary alarm reg 1. This is the actual is it the same as is it temporary register only? Okay. So this is advancing that particular very same register. If you want to advance, you need another signal, is that right? And you need 6 such registers here, and you also need to reset we have not seen reset. For same registers we need reset here, and that is up to this. And now comes the independent alarms. For example, alarm 1 and reg 1 through 6 you have. This is for this corresponds to the counter 1 through counter 6 or counter 7 through counter 12, which is the one second one, no? Counter 7 through 12, right. This corresponds to that. It is not the same, it is different from the counter 7, but it has a similar meaning to that, right. This is exclusively for setting the alarm. You have 3 different alarm that can be set, right. And as I mentioned, in for epilepsy patient we need to set 3 times, say at morning 7 o'clock, and then afternoon 1 o'clock, and then again at dinner time, say 8 o'clock. And if they miss the tablets within half an hour, if they do not take, they will promptly get fits. So in order to overcome that one, you can have 3 different settings. So we have alarm 1 through alarm 3 here, so alarm 2 here and alarm 3 here. And for you also need advance hours temporary alarm, you have to advance them. So and for hours, minutes, seconds you have to advance, and 2 digits will run independently. You have to set hours separately apart from minutes and seconds. And you also have one set alarm, and that is declared as wire, and one alarm is there, this register here, alarm read set also you need. And you have display time, display stopwatch, display alarm. When we go into details, we will see more about this. We also need to sound the buzzer. For that we need some 30 seconds counter, and after end of which the buzzer will automatically stop. You do not have to redo any resetting, etc. Everything is automatic. If you want to introduce more automation, you are free to amend the codes, and after you learn this. And you also need delay, another register, and you want to match for independent alarms. So for that another signal is required. This goes high when the runtime matches the alarm 1 set point. How to set, etc. we will be seeing. And we also need alarm 1 30-second counter next. This is for pre-incrementing the counter. And if you want to advance alarm 1 30-second counter, this is the real counter which runs, and this is the pre-increment for this. And you have similarly alarm 2, and exactly the same thing signals you have here for alarm 2 all up to this. And so is the case for alarm 3 here, right up to the match and counter and so on. So you also need registers for beep and ring. They are all single bit, and this is a buzzer we are going to connect. And in order to do the beeping, we need to have another counter. 3 bits are adequate for that counter, and you need to pre-increment, so you need this as well. And we have some more registers and term count reg 1 through reg 6 for use with up counter. When you set the up counter terminal count, I think you need this, right. And you also have another terminal count for next up to this here, and then you need advance the terminal count register, and as well reset, once again advance reset for each of the 6 registers that you have here. And you also need advance hours. TCR here means terminal count register. You need some more signals, and terminal count reach for up counting. If it is reach, this will be indicated. If it is down counting, the terminal count reach, when the set delay matches, that is what we mean. So this will be done, and they are all wires there. And you need a timer out alarm counter, which is a 30 seconds counter for audio alarm. And once again pre-increment, then timer out alarm is there, and the real time clock implementation starts here. And you have any specific question? Let us clear that first, because we have just finished the declaration. So only in the next lecture I think we should take it up, so that we are fresh from the actual core is from starting from here. So far what we have seen is only the declaration.
You said it's not required to press the buttons independently to set the time for up down counting. If the button is kept pressed for a long time, you can advance the count. Can you please explain how this is exactly done in the code again?
Not right in the code. Let us go back to the actual layout that we have started with. That was here. For the layman, I said we have to have this. Let us understand this here. See, we want to set, let us say, hours, minutes, seconds. So, how do you go and set it up? Now, we want to, let us say, what do you want to set? Do you want stopwatch to be set or a timer to be set? Please come out. What you want really? Stopwatch. Okay. So, you just set it in set here, then stopwatch, right? Make sure that these things are all off. Preferably this is in read and this can be off, and this also preferably off, right? So, what is going to happen is we want to set the stopwatch. How much time do you want to set? 20 seconds. 20 seconds. Okay. So, what all we need to do is we just press this. So, when you press, each time you press and release the button, this will advance by 1. For example, 0, 1, next time you press it will be 0, 2, 0, 3 and so on. And this is a very tedious thing. If you want to set up to 59, if you want to set, it will be a tedious process. You have to press 59 times. In order to relieve your burden of the burden, so what we do is we just you just press once and hold it. If you press, having pressed once, it code will recognize and advance by 1, and then it will continue to see whether you are continuing to press for 2 seconds and more. If it is beyond 2 seconds, it will start running at a very rapid space. Automatically it will roll. So, it will advance 10 times faster. For example, this will become 1, 2, 3 every second instead of this one. So, you have a provision of setting fast. So, here 1, 2, 3, 4, 5 when you come, you release the thing. Then you would have got almost 51, 52. You have no control over that. So, then after that, suppose you want to set 59 seconds instead of 20. You are now at 52 test stop, and now you keep on advancing only 6 times. And that is precisely what you have here in the timer also. The buzzer has gone because it is right time. Okay. Does it answer your question? Thank you.